Hello everyone, welcome to the webinar for AI Engine Development using Vitis Model Composer. In this webinar, I will explain the AI Engine development flow using Vitis Model Composer. We will see what is Vitis Model Composer, then the various libraries available, development flow using Vitis Model Composer, and finally some key points are given as the summary. At the end of the presentation, I will demonstrate the AI Engine development flow using Vitis Model Composer. Versal Adaptive Compute Acceleration Platforms (ACAPs) combine scalar engines, adaptable engines, and intelligent engines with leading edge memory and interfacing technologies to deliver powerful heterogeneous acceleration for any application. The AI Engine Array is the top-level hierarchy of the AI Engine architecture. It integrates a two-dimensional array of AI Engine tiles. Each AI Engine integrates a very long instruction word processor, integrated memory, and interconnects for streaming, configuration, and debug. One of the way to program Versal ACAP device is using model-based design environment. We have Vitis Model Composer, which is based on model-based design flow. Our focus on this webinar covers the AI Engine development using Vitis Model Composer. Model-based design is a mathematical and visual approach for developing complex systems. With the model-based design, virtual models are at the center of the development process to improve how you deliver complex systems. Using model-based designs with the MATLAB and Simulink software, you can shorten development cycles and reduce your development time by 50% or more. The main advantages of the model-based designs are you can try new ideas and perform fast, repeatable tests with modeling and simulation. You can eliminate manual steps and reduce human error by automating key steps such as reporting, coding, and verification. The path from algorithm to implementation on FPGAs and adaptive SoC devices is not straightforward. Let's take a quick look. The first step of any product development is requirements gathering from the algorithm exploration and design phase. Every company has an algorithm development team. These are domain experts. The focus of these developers is using a high-level language to express the algorithm and create a proof of concept of their product. This is also where MathWorks' flagship tools, MATLAB and Simulink, come into the picture. Now making a transition from algorithm to implementation on FPGAs, SoCs, and ACAPs often requires rethinking. You need to modify the algorithm to make it better suited for hardware targets and explicitly take advantage of their parallelism. In the traditional design, once the algorithm has been designed, the algorithm developer would hand over written specifications to the RTL or hardware engineer to take care of everything that would be needed to implement this algorithm on the FPGAs, SoCs, or ACAPs. A lot of time is spent in re-implementing the high-level algorithms into low-level implementation models. This creates a barrier to entry for domain experts and also forcibly elongates the design cycles. So as you can see, there is a huge gap between the algorithm developers and the hardware engineer. The skills and domain knowledge on both sides are not same. Some of the points that results from this gap include the need to re-implement an algorithm for efficient mapping to the architecture. Hardware specific decisions to be made. As the design becomes more complex, simulation performance becomes a bottleneck, which limits the parameters for which the design can be tested. Another point is the testing of functional equivalence. How will you know that the high-level algorithm designed is same as the implementation in the hardware? And this also makes it more difficult to debug issues with hardware implementation. So it is important to provide an easy path from algorithm to implementation and to bridge the gap. Vitis Model Composer, a high-level abstraction design tool, is designed to solve some of these challenges. It provides better integration from algorithm to implementation for algorithm developers who use the MATLAB and Simulink environment. Vitis Model Composer provides a library of performance optimized blocks for design and implementation of algorithms on Xilinx devices using HDL, HLS, and AI Engine blocks. System Generator, the previous standalone design environment for developing DSP algorithms and generating HDL as an output, is now part of Vitis Model Composer. Furthermore, you can develop new algorithms by using the HDL library, HLS library, and AI Engine library. Vitis Model Composer in a nutshell. In short, Vitis Model Composer allows you to drag and drop AI Engine and programmable logic optimized blocks from the Simulink library browser, co-simulate designs with PL and AI Engine blocks, generate HLS, RTL, and data flow graphs as well as test benches, move your design into hardware with a click of a button. In the Xilinx toolbox, you can see the AI Engine, HDL, and HLS library blocks. The AI Engine library in Vitis Model Composer contains blocks to import kernels and graphs that can be targeted to the AI Engine portion of Versal devices. Also included is a set of complex AI Engine DSP building blocks related to FAR, FFT, DDS, and mixers. The tool transforms your AI Engine design specification into a top-level connected graph to implement AI Engine based devices. You can see here on the left AI Engine library under Xilinx toolbox. In the middle, you will find the categories available under the AI Engine library. And finally, you can see the various functions that are available under DSP Stream IO blocks. You can see here on the left HDL library under Xilinx toolbox. In the middle, you will find the categories available under the HDL library. And finally, you can see the various functions that are available under DSP non-axis stream. The HLS library in Vitis Model Composer offers predefined blocks that include functional blocks for math, linear algebra, logic, and bitwise operations. The tool transforms your algorithmic specifications to production quality implementation through automatic optimizations that extend the AMD Xilinx high-level synthesis technology. You can see here on the left HLS library under Xilinx toolbox. In the middle, you will find the categories available under the HLS library. And finally, you can see the various functions that are available under math functions, math operations. You can even import your custom code as a block. It can be RTL, AI Engine kernel and graph code, and HLS code. Once the custom code is imported, it becomes as any other blocks. Then it can be used as part of subsystems. These custom blocks can be connected to other blocks in the Simulink library. Using the MATLAB and Simulink environment, you can design, analyze, and visualize your design. Here is how you can do it. Create block designs. By using the optimized AI engine, HLS, and HDL blocks directly from the Simulink library browser, or by importing custom AI engine, HLS, and HDL code as blocks if required. Verify the block designs. Run fast simulations in the Simulink environment. Then compare the results with golden references in the MATLAB and Simulink tools. Analyze and debug your designs. You can easily tap into intermediate signals, debug and get visibility into the design. You can co-simulate a heterogeneous system that includes AIE and PL blocks. You can directly use optimized AIE, HLS, and HDL blocks from the library browser, or import code as blocks and then seamlessly connect all the AI engine blocks with HLS kernel blocks, or connect AI engine with HDL blocks. Once the connection is done, you can co-simulate the AIE plus PL blocks and verify the results. Most of the HDL blocks have equivalent cycloaccurate C model to verify the RTL for a faster simulation. In some cases, it may use the XSIM to simulate the blocks where the C model is not available. For HLS blocks, it uses the CSIM, which is bit accurate but not cycloaccurate. Similarly, AI engine blocks are simulated using the x86 simulator for faster verification, which is bit accurate but not cycloaccurate. You can increase productivity by generating code from your design. Using Vitis Model Composer, you can generate different types of codes, including RTL, Verilog and VHDL, optimized HLS code with inserted pragmas, test benches, and ADF graph and test bench. You have the following options to package your design files for HDL. HDL netlist generates VHDL or Verilog RTL designs. IP catalog packages the design as an IP core that can be added to the Vivado IP catalog for use in another design. Synthesized checkpoint creates a design checkpoint file that can be used in any Vivado IDE project. For HLS designs, you can package the design files into IP catalog or as a source code. For AI engine designs, generates ADF graph and make file. You can also easily validate your design in hardware. Generate the data movers, PS code, and configuration file. Generate the make files needed to build a design for hardware. Move the design into hardware with a click of button. Before going into the details for creating an AI engine design, let's take a quick look at the AI engine library blocks. The AI engine library is available under Xilinx Toolbox in the Simulink library browser set. The AI engine library includes various block sets as shown here. These block sets are classified under categories such as DSP, interfaces, signal routing, sync, sources, tools, and user-defined functions. The Vitis DSP library is a library of commonly used DSP functions optimized for AI engines. To facilitate the use of these functions in a design, Vitis Model Composer provides different DSP-lib functions as blocks in the Xilinx Toolbox AI Engine DSP library. Vitis Model Composer provides a copy of DSP-lib functions that can be used as is. This is in sync with the DSP functions available in Vitis libraries GitHub. Optionally, you can download DSP-lib functions from the online GitHub repository and use the MATLAB tool command xmc library path to set the path to the DSP-lib library. Vitis Model Composer supports importing C or C++ kernel functions, provided these functions have void as the return type. Importing class kernels as well as templatized kernels is also supported. Model Composer provides two AI engine library blocks to import kernel functions of different types. The AI engine kernel block, non-class based, and the AI class kernel block for class based. AI graph. The AI graph block also allows you to import an AI engine program that consists of a data flow graph specification written in C++. Now, if you have a data flow graph instead of an AI engine kernel function, then Model Composer allows you to import it into the Simulink environment, from where it is possible to seamlessly connect the AI engine graph block with AI engine kernel block to build a complete system. In summary, the entry point for using an AI engine block set can be a kernel or a data flow subgraph, for which Vitis Model Composer generates a block with interfaces that match the function arguments of a kernel or a graph. Constraints are user-defined properties for graph nodes that provide additional information to the compiler. Vitis Model Composer provides a mechanism to specify these constraints from within the kernel import or graph import blocks in the AI engine library. During graph code generation, all constraints automatically appear inside the graph code. You can access and specify constraints from the Constraints tab of an AI engine kernel block by using the Open Constraints Editor button. This opens the Vitis Model Composer Constraints dialog box. The AI engine kernel development flow has been described here. The user has to import the kernels as a block and connect to the source and sync. Then run the simulation and verify the output by comparing with the golden reference, which can be generated using the Simulink models. If the design does not match the output, modify the kernel code and again run and verify the output until you get the desired results. Once the functional correctness is verified, then the next step is to generate the code and run the AIE simulation. You can verify the throughput and performance metrics using the Vitis analyzer. If you have not achieved the desired performance, perform the following, such as modify the code, add or modify the constraints, and add FIFO blocks. After doing the modifications, again perform functional verification to make sure the changes are not affecting the correctness of the output. And then again generate code and verify it by running the AIE simulation. Vitis Model Composer is a model-based design tool that enables rapid design exploration within the MathWorks, MATLAB and Simulink environment. Vitis Model Composer provides a library of more than 200 HTL, HLS and AI engine blocks for the design and implement it on FPGAs and adaptive SoCs. Vitis Model Composer allows you to create, analyze, and debug your design. You can co-simulate AI engines and PL. It allows you to generate the code and validate it in the hardware. Also, Vitis Model Composer supports import of your custom code as a block. So that's all for this webinar presentation. For the next steps, welcome to access the download page for the latest Vitis product release. Also, we encourage you to access our GitHub repository to get more Vitis tutorials and example design. In this demo, we create an AI engine application using the AI Engine DSP library blocks from the Vitis Model Composer. Then we simulate the design, import a custom code as a block and verify the design. Once the functional verification is done, generate the code and perform AI Engine emulation and debug the design to achieve required performance. Thanks for watching the presentation. Next we will watch the demo. This demonstration shows how to create an AI Engine application using the AI Engine DSP library blocks from the Vitis Model Composer. There are 7 steps in this demo. In step 1, we add one FAR off-band decimator filter block and provide the simulus to the block. Also, we use the equivalent Simulink model to verify the output of the AI Engine block. In step 2, we run the simulation and verify the design. In step 3, we will add 2 more FAR off-band decimator filter and FAR symmetric filter in cascaded form. In step 4, again we run the simulation and verify the design. In step 5, we import the AI Engine custom code and connect this block to the rest of the system. In step 6, again we run the simulation to verify the output. And in step 7, finally we generate the code and run the AI Engine simulation to analyze the performance. In this step, we will add the FAR off-band decimator filter block and configure the parameters. In this demo, we are using 2022.1 version of Vitis Model Composer and MATLAB version R2021B. Now we are launching the Vitis Model Composer. The design files are already downloaded from the Vitis-Tutorial Github page. Let us run the setup lab function, which will create the variables for the filter coefficients. We use these variables in configuring the filter parameters. Let's create a blank model. You can see the libraries available under Toolbox, that is AIE library, HLS library, and HDL library. Browse under the AIE library and add the block FAR off-band decimator. Update the block parameters by double-clicking the FAR off-band decimator block. Create a data source to feed this filter. Select the random source block to add the block to the design canvas. and update the block parameters. Similarly, add a cast block and update the cast block parameters. We need to verify the output of the block by golden reference model. Here is a Simulink model which will be added to the design to cross-verify the generated output. Copy the HB1 block from the reference chain design. Copy the two fixed size, subtract and scope blocks from the reference chain design. Set the output size parameter to 1024. Now run the simulation and verify the output by comparing the results with the equivalent Simulink blocks. Change the stop time setting to 5000 in the simulation tab. Simulate the model. Observe there is no difference between the AI Engine filter and the Simulink tool filter output. Update the display parameters to provide more information about the signals. Notice that before implementing the decimation filter, the vector length was 2048, but after implementation, this is reduced to 1024. In this step, we add two more FAR off-band decimator filters and one FAR symmetric filter in a cascaded form, and then configure the block parameters as listed here. Add two FAR off-band decimator blocks and configure the parameters. Add a FAR symmetric filter block and configure the parameters. Add the equivalent Simulink model blocks which will be used to cross-verify the generated output. Update the output size to 256. Now again run the simulation and verify the output by comparing the results with the equivalent Simulink blocks. Simulate the model. Observe there is no difference between the engine filter and the Simulink tool filter output. Analyze the design using the spectrum analyzer scope. Select the spectrum analyzer scope and connect the spectrum analyzer scope at the output of the last AI engine filter, that is FAR symmetric channel filter block. Change the stop time setting to infinity in the simulation tab. Run the simulation and observe the output in the spectrum analyzer scope. In this step, import the custom AI engine kernel code. Connect to the system as shown here. Then run the simulation and verify the design. Import the frequency shift kernel function into the design. Add the header file, kernel function, and kernel source file details. Configure the parameter values. In this case, the window sample size is 256. Connect this block after the FIR symmetric filter block. Add the equivalent Simulink model blocks which will be used to cross-verify the generated output. Simulate the design. You can observe that the frequency shift in the spectrum. Observe there is no difference between the AI engine filter and the Simulink tool filter output. Once the functional correctness is verified, then the next step is to generate the code and run the AIE simulation. Create a subsystem which will include all the AI engine blocks. Rename the subsystem as FIR chain. Add the Vitis Model Composer hub block and double-click it to configure the code generation settings. Select the target subsystem and then select the required options. Now generate the code by clicking the generate button, which will also run the AIE simulation. Here you can see the test passed message by the AIE simulator. Note that the estimated throughput is 44 MSPS instead of the expected 100 MSPS. We will now fix the estimated throughput issue in the application by customizing the PLIO blocks in the design. To fix this, we have to increase the input bit width from 32 bits to 128 bits. Connect the PLIO blocks to the design. Now again generate the code and observe the throughput. You can see the PLIO width in the Vitis analyzer. Note that the estimated throughput is now 177 MSPS instead of the previously calculated 44 MSPS. In this demo, we have learned to create a vessel AI engine application using the AI Engine DSP library blocks from Vitis Model Composer. We have imported the custom code and simulated the complete system. Then generated the graph code from the AI Engine subsystem and analyzed the performance of the design.